Welcome to The Explainer. Today, we're diving into something that really challenges how we think about engineering. If you want to master the extreme, ultra-low temperature environments required for cutting-edge quantum technology and dilution refrigerators, you absolutely have to master the materials that make it all possible. We're going to be looking at the ultimate odd couple of the sub-1 Kelvin world. We're talking about two drastically different materials that must work perfectly in the exact same apparatus, but under strictly orchestrated rules. To really understand why these materials are so vital, you have to appreciate the extreme environment we're dealing with, minus 269 degrees Celsius. Let that sink in. We are talking about temperatures pushing the very edge of absolute zero. In this high-stakes reality, standard engineering rules go completely out the window. Normal plastics, they shatter like glass. Standard rubber O-rings, they turn into brittle rocks and fail catastrophically. Okay, let's dive into this because the cold isn't even the only challenge. This tiny number, 1 × 10 to the negative 10 torr, represents the ultra-high vacuum hermeticity required in these systems. You see, the delicate cold stages of a dilution refrigerator, where the actual physical quantum experiments happen, must be perfectly, flawlessly isolated from ambient room conditions. A single failure here means your experiment never even gets off the ground. So the ultimate question becomes, how do we trap absolute nothingness at the edge of absolute zero? Frame this in your mind as a thrilling, high-stakes diffusal mission. Experimental physicists are constantly fighting to prevent even microscopic leaks from destroying years of quantum research. And to win this fight, they rely on a very specific set of tools. Section 1. Sealing the extreme cold and the metal. Let's meet the first character in our odd couple. This is the boundary guardian, trusted to hold the line against the outside world. This silvery, self-passivating metal is indium. In the construction of cryostats and inner vacuum chambers, indium wire is universally trusted. It is the absolute gold standard for cryogenic vacuum seals. But to understand why it's so uniquely qualified for this job, we really need to look at its physical properties. Now, what's really interesting here is its unmatched malleability. Indium has a Mohs hardness of just 1.2. Just to put that into perspective, compare that to copper at 2.5 or aluminum at 2.9. Because it's so incredibly soft, it conforms completely to the microscopic imperfections of mating flanges. And even better, it retains its integrity all the way down to those cryogenic temperatures without suffering from mechanical failures caused by differential thermal contraction. Plus, because it requires such low compressive force, cryostat designers can use smaller profile flanges and fewer screws. That is a massive advantage when you're trying to save space and reduce thermal mass. And this brings us to the actual mechanism of the seal. Indium doesn't just sit in a gap like a rubber gasket. It goes through a true metal-to-metal cold weld. When you compress it between two flanges, the metal undergoes extreme plastic deformation. It literally flows like a thick liquid under pressure, filling absolutely every microscopic surface gap without the need for any heat. It merges directly with the flanges. Section 2. Apiezon N. The thermal bridge. But trapping the vacuum is only half the battle. Once you're isolated from the outside world, you still have to efficiently cool everything down inside. Enter our second character, Apiezon N. This acts as our thermal bridge. It's a highly specialized, tenacious substance that is wonderfully pliable at room temperature, which makes mounting delicate components super easy. But as it cools down to cryogenic temperatures, it solidifies securely, holding and protecting delicate sensors without causing them any physical damage whatsoever. The superpowers of Apiezon N are truly remarkable. Most greases turn brittle and craze or crack at extreme cold, which entirely ruins a vacuum. Apiezon N, it remains completely crazed-free. It has a spectacularly low vapor pressure, making it perfectly safe for ultra-high vacuum spaces. Furthermore, it's a silicone-free hydrocarbon. This is absolutely huge. You see, silicone greases suffer from something called creep, where the silicone slowly migrates and contaminates adjacent surfaces. Apiezon N stays exactly where you put it. It even has a gettering action, meaning it absorbs stray chemical impurities right off the metal surfaces. But its main job is bridging the microscopic gaps. If you bolt a copper wire to a cold plate, no matter how smooth they look to the naked eye, on a microscopic level, they are like two mountain ranges crashing together. Only the highest peaks actually touch, leaving microscopic valleys filled with trapped air. Apiezon N fills those micropores, drastically reducing the interfacial thermal impedance. It's literally the ultimate thermal coupling medium.
Section 3. The contamination conflict.
And this brilliantly illustrates the core conflict here. If both of these materials are absolutely perfect for the exact same sub-1 Kelvin environment, should we combine them? Well, looking at their underlying nature shows why that instinct is completely wrong. Indium's superpower relies entirely on forming an oxide-free, pure metal-to-metal cold weld to act as the vacuum boundary. Apiezon N, meanwhile, is an organic hydrocarbon acting as a thermal medium. Their functions are entirely different, and physically they are completely incompatible at the sealing interface. To understand exactly why, we have to look at the 80 angstrom thread. Indium is self-passivating. Just sitting in a room, it naturally forms a native oxide layer on its surface about 80 to 100 angstroms thick. Now, this oxide is brittle. It's much harder than the pure indium underneath. If you don't remove this oxide before compressing the seal, that brittle crust gets forced directly into the soft metal, creating stress risers and microscopic flaws that will inevitably fail when repeatedly cycled down to extremely low temperatures. So the absolutely crucial point is this. Indium demands absolute purity for its cold weld. Apiezon N grease, despite being a total miracle material for heat transfer, is an organic hydrocarbon. If you interpose it on the primary sealing interface, basically if you put grease on your indium wire, you are acting directly against the physics of the cold weld. You've just introduced a massive contaminant. Greasing the wire will completely ruin the flawless metal-to-metal bond and cause catastrophic cold leaks when you chill the system down. Section 4. The expert protocol. Let's move along and see how this all builds together. How do the pros actually handle this diffusal-like situation without ruining the seal? First, you meticulously clean the flanges and completely remove the indium oxide using a solvent or a fine silver polishing pad. Second, you overlap the bare, pure indium wire right in the sealing groove. Third, and this is where Apiezon N comes in, you apply the grease strictly to the bolt threads or the external thermal anchoring points to ensure the flange reaches base temperature quickly, but absolutely never, ever cross the streams. The Apiezon N must never enter the indium compression path. Finally, you compress the seal evenly with opposing bolts. It's an incredible synergy of materials, isn't it? The pure, conforming strength of indium keeping the entire universe out, and the pliable, heat-sinking tenacity of Apiezon N keeping the inside cold. They are kept strictly separate, yet working beautifully together to enable the impossible. As we push the boundaries of quantum technology and ultra-low temperature physics, it really makes you wonder, will your next massive world-changing breakthrough rely entirely on mastering the microscopic details you learned today? Think about that next time you see a dilution refrigerator in action. Thanks for joining me on this explainer, and keep questioning the details.